Okay, so for Unit 10, we're starting with equilibrium, and you just saw the lamest demonstration ever. And now let's apply the lame demonstration to some actual numbers. First thing I want you to see is how you recognize if something's a reaction that's an equilibrium reaction. Well, there's already a typo in my notes, so we need to go ahead and make this a double-headed arrow, okay? So go ahead and add that. So we already talked about an equilibrium reaction is a reaction in which the forward and reverse reactions are happening at the same rate. So there is not going to be a change in concentration of reactants or products. We can mathematically represent this with something we call the equilibrium constant. Here it's called Kc. If you just see K by itself, that's assumed to be Kc. There's also something called Kp, which is the exact same ratio, but we use pressures instead of concentrations, and both are acceptable. Do y'all remember why we can substitute pressure for concentration? Do you remember the use of Pervnert? If I isolate, I know I've done this before, if I isolate my P there, what's N over V? What? Moles per liter, which is known as molarity, so that's a concentration. So pressure is equal to concentration, and it's proportionally equal with this RT being the proportionality constant. So we can interchangeably use concentration or pressure in this expression. So what is the expression? It is the concentration or pressures of products divided by the concentration or pressures of reactants, raised to the coefficient in the balanced equation. So you have to know how to set up your expression. When I say expression, I'm talking about unsubstituted, an equation that's unsubstituted. This would be an expression with no numbers in it. So this is going to be a requirement for every equilibrium problem you do, because that's usually your first point out of 10. One thing I failed to mention about this concept of equilibrium, we have Unit 10, which is equilibrium, Unit 11, which is acid-base equilibrium, and Unit 12 is when we get into buffers and titrations. All of those units make up what's going to be on question number 1 on the free response of the AP. Okay, so we're going to really focus on that because I know for sure it's coming, and so these units tie together. Unit 10 is easy, 11 is a little bit harder. Unit 12 is going to kick some booty. All right, so we want to make sure you understand this pretty clearly. So going back to this, if I look at what this is a ratio of products over reactants, we can determine what reaction is favored, forward or reverse, based on the magnitude of that number. So let's say I have a reaction where I'm producing more product. I've produced more product and I have less reactant. What's the magnitude of K? K would be greater than 1. So what does that mean? Forward or reverse is favored? If K is greater than 1, it means I have more product. More product means the forward reaction is favored. And I believe I say that down here. When K is greater than 1, the amount of products is greater. Okay, and the forward reaction is favored. I'm going to make sure that that's written there. The reaction favors the products, right? So that's forward. Right, and then if K is less than 1, it means we have more reactant. If we have more reactant, that means that we favor the reverse. So everyone turn around and look back at our pots. If the left one is reactants and the right one is products, what's favored, forward or reverse? Reverse, so more reactants means K is less than 1. And so that would be a way for us to tell. Now, a lot of people say, what do you mean by favored? Why would a reaction be favored over another reaction? Well, what I'm about to tell you is very rudimentary. There's so much more to it. This is like the most simplistic way to explain it. It doesn't take into account entropy and enthalpy and all these different things. But simplistically, if we had 3 A's plus 4 B's in equilibrium with a C, let's pretend, okay? If you look at this reaction going in the forward direction, 3 A's would have to combine with enough energy with 4 B's, all at the right orientation, to make a C. Does that sound easy or a little difficult? Yeah, hard. In comparison, think about the reverse reaction here. If we were going this way, what does C have to do? Break up, decompose. So that's pretty simple. So which is favored? Which is going to probably produce more, the forward or the reverse? The reverse. So if the reverse is favored, we make more reactant. What can we assume the magnitude of K would be for something like this? Perfect. K is less than 1. Again, you're not going to be able to count molecules and do this. I'm just kind of giving you an idea. There's so much more involved with this than that. And this is just kind of why reactants might be favored over other reactions. Okay? So let's go into the actual math here, the fun part. And we're going to solve for a K. The following reaction is at equilibrium at a particular temperature. And they give you, notice, all these concentrations are equilibrium concentrations. Our reactions happen just like the fish tanks back there. We're done. We're at equilibrium. These are the concentrations at equilibrium. They say calculate the magnitude of Kc. So I'm going to require in all of your stuff that you write the unsubstituted expression first, because that's always required. So how do I set up this expression? Products over reactants. And again, I'm a bad teacher. I failed to talk about what we can and cannot put in this expression. There's a very important point I failed to mention, and that is the following. These are concentrations, right? So we know that we can have solutions with concentrations like AQ. Gases can have concentrations. What can't have concentrations? Solids are pure. You can't have solids. So if you have a solid in an equation or a pure liquid in an equation, you do not put those in the equilibrium expression. They don't go there because they do not affect the equilibrium. Their concentration is so high because it's pure, it's not affected enough to vary. It doesn't vary enough to change what's going on. So we leave these guys out. So we leave solids and liquids out of the expression. They do not affect equilibrium. So now we can go, knowing that these are all gases, okay? We're doing Kc, so Kc is concentration. We have the concentration of Hi. What do I do to that? Raise it to the coefficient in the balanced equation. Divided by the concentration of H2, raised to the first, divided by the concentration of I2, raised to the first. Now, people say, what happens, don't write this down, but they say, what happens if something's a solid? Let's pretend it's not. But if that were a solid, we would have 1 over. Okay? That's when I say leave it out, that's what I mean, leave it out. It doesn't go in there at all. But that's just an example. That's not the truth here. So, okay, so now how do we actually calculate for Kc? This couldn't be any easier. Plug and chug. Hi is 0.3. O, we're going to square it. H2 lets you 0.012 to the first, and I2 is 0.15 to the first. So you see why having a balanced equation is crucial for this kind of thing. All right, what's the magnitude of Kc, or what's the actual value of Kc? Give me 2 sig figs, please. 50. How do I make that 2 sig figs? Put a point. And here's the best news of the day. This is probably the best news of your life. Yay! Units are not required on equilibrium constants. So we need units on kinetics Ks, yes, but we do not need units on our equilibrium Ks. Because the magnitude of the 50 just tells us all we need to know. The units on K in kinetics, you know, that told us, or we could figure out order from that. We could learn a lot from looking at the units. We know all we need to know by the fact that Kc is 50. Okay. One other thing I want to talk about with these Ks. Ks are temperature dependent. So if we are at a different temperature, we need a different K. So just know that Ks are only good for a particular temperature. If you run a reaction at room temperature, that's what the K is good for. All right, I'm not going to do any more of just the plug and chug expression stuff. We're going to get plenty of practice with this in the next few days. What I do want to do now is talk about how to convert back and forth between Kp and Kc. We know that both Kp and Kc are products over reactants rates of the coefficient, but one is concentrations and one is pressures. We can convert back and forth through, and I'm not going to go through this. We already gone through it before, but this shows you again that if you had perv-nert, we get concentration there, that the proportionality between the two is RT. And so if you take all those concentrations in a normal expression and replace it with what pressure is equal to, you can dilute it down to this. And what I call this is the politically correct equation. I had a hard time before I did politically correct remembering, was it Kc is equal to Kprt, or was it this way? It's politically correct. See that? It works. It helps. Do you really see it? Okay. A little slow today, maybe. So politically correct. Kp is Kp, Kc is Kc, so you'll be given one of those and told to solve for the other. R, since we're dealing with perv-nert and gas laws, is going to be the gas R. So that's 0.0821 lattimolk. What do you think our temperature unit has to be in? K. K as in Kelvin, not K as in. A friend of mine, a teacher that I work with in the summers, taught chemistry for the first time. She's mainly a biology teacher, but she was very stressed out about the number of Ks in this class. We've got the Kelvin, there's K, Ka, Kb, Kc, Kp, Kw, then the K in kinetics. So there are a lot of Ks. It's true. But anyway, this delta N right here, you've seen it before. You saw it in that delta E is equal to delta H. It's that equation. Exact same thing. What was it? Change in moles of, more specifically, gas. Again, we're dealing with pressure, so gases are the only things we care about. So this is the change in moles of gas. Using the coefficients, we take the moles of product gas minus moles of reactant gas, and we raise it up. And you only raise RT to the delta N, not the whole KRT, just RT. So let's apply it. You'll see it's not that bad. It says at 1100 K, Kp equals 0.25 for the reaction, and the sulfur trioxide is a gas. Calculate K at this temperature. All right, so we're going to do politically correct. Politically correct to the delta N. I was trying to figure out a way to work in the delta N to that. I don't know. I couldn't come up with anything. So we have Kp. We're solving for Kc. What was R again? Lattimolk. I shouldn't do parentheses. And then what is the temperature? 1100 Kelvin. And then we're going to raise that product to the delta N. So go to products. How many moles of gases are on the product side? 2. How many moles of gases are on the reactant side? 3. There we go. Go ahead and solve. All we need to do is use 2 sig figs there. So we get an answer of 23. And again, you don't need units. I know it feels weird not having units, but enjoy it. It's one of the few times you get to do that. All right, questions on that? Let me ask you, when would there be a situation when Kc would be equal to Kp? Look up there. When? Perfect. When you have the same number of moles of gas on each side, you have your delta N is equal to what at that point? 0, right? And so that takes that delta N, RT to the delta N, Anything to the 0 power is 1, right? So that just drops it right out. So that means therefore Kc is equal to Kp in that case. So this is the trick to this. I really need you to check that delta n first before you do any work, because if a problem like this were to show up in the non-calculator section, you might panic and go, oh, I can't do politically correct. I don't have my calculator. I bet you $1 million delta n is 0, and you can do it. Okay, so always check that delta n before you actually start your work. Because if you see that that's 0, you can just immediately, without even plugging anything in, say there's no change of moles of gas, therefore Kp equals Kc. Got it? All right, next. This is fun. You're going to like this. It's like a puzzle. Jasmina doesn't look happy. What's wrong? So we just had a very enlightened discussion. I paused the video and I've unpaused it, that we can make our delta n be changes no one. So you said nobody. I can't go with that. I'm going to go with no one. So political correctness changes no one. There's our delta n. Good job. Yay, Jasmina. Woo. Okay. So now we're looking up at this. I just want you to focus right here. And we'll break this down a little bit at a time so it's not overwhelming. It's actually kind of cool. So if you're given this reaction, and we're given the K of 50, you know that the expression you'd use to represent this would be products, HI squared over reactants, right? And they give you the value of 50. You can utilize this 50 and find Ks of other similar reactions by algebraically manipulating that number. For instance, look at this equation right here. How does that differ than that? What did they do to this equation compared to the above one? It's reversed, right? So if we reverse the equation, think about what this is. It's products over reactants. Looking at this, what do we do to the expression if the equation is reversed? Flip. What's the flip called in algebra? Reciprocal. You take the reciprocal of the K. So if the equation is reversed, you take the reciprocal of K. I don't know if I spelled reciprocal correctly. I can't spell. That's not shocking to you, all I know. You've seen me do some horrific things. Okay. Understand that? We don't negative it. We don't, like in thermo, we would have changed the sign. We don't negate it. We actually flip it. I like negative it. All right, looking at this next one. Again, we're referring back up to this equation. What did we do from there to there? We divided it all by 2, or you could say, I'd prefer if you just go ahead and think multiplying by a half. We multiplied everything by a half, correct? What did those coefficients, how were those translated to an expression? The coefficients were used as what? In any expression, as a power, as an exponent, right? So look at this expression and look at this. Do you see how each expression is multiplied by a half as well? So what you end up doing is whatever you multiply your equation by, you raise your K to that same power. So if equation is multiplied by, I'm going to put X, raise the K to the X power. Does everyone kind of understand that? See why that happens? And that's what they did here. We took the 50 and we raised it to the half, which is square root. That's why there's a square root there. We'll practice. Pretty clear? Clear as crystal, or as clear as mud, as my dad used to say. My dad said some really strange stuff. That wasn't one of the strange things he used to say. All right. The last one. This is fun. is what do we do to k's when we add equations? So looking at this equation, does everyone agree that B over A is the correct expression? Right? It's the gases, don't worry about that. Does everyone agree that D over C is the correct expression? So when I add these two equations up, I get A plus C, and I get B plus D. Now before you even look at any of that, does everyone agree that the correct expression for that is D times B over A times C? That's correct. So how do I go from there and there to get this? We multiply them. So if you add equations, you multiply their k's. All right, let's see this in action. Action Jackson. They give you they're equilibrium equations, and then they give you the k for each one. This is a lot like that thermodynamics stuff we did, the flippy thing. This is the same thing, except we have to treat the k's a little bit differently. So this is our goal, and we want to know what the k then is for the goal. And notice it says calculate k at the same temperature. Remember, k's are only good at a particular temperature. So what do I want to, I'm going to start with the first equation. What do I want to do with that equation? You know this from thermo. What do we want to do with it? It's a sole source of water and H2, right? So what do I have to do to it? I'm going to flip the first equation. So I get CO plus H2O gives me COO plus H2. Since I reverse the equation, what do I do with the K? No negating. That's thermochemistry. Remember, products over reactants is the equilibrium expression. Reciprocal. So we do 1 over 67. Be careful. Don't fall into that trap of making it negative. That's thermochemistry. Exothermic becomes endothermic. Okay? Because remember, this is a product over reactant issue. Okay. What do I do with my second equation? We want to flip it? I think it's good where it is, right? Because that'll let me cancel some stuff out. So I'm going to do I need to? No, I don't think so. So I'm going to leave it as is since I didn't change it. So I'm going to leave the K as it is. And just to make sure I get my goal, I want to add these up. That cancels. That cancels. So I get H2O plus CO gives me H2 plus CO2. Does that match my goal? Yes, it does. So because I went ahead and successfully added these, what do I do to my K's? Multiply them. So what's 490 divided by 67 and give me 2 sig figs? 7.3 is equal to my K3. Yay. That's not that bad, right? We have one more problem to do for the day. It's an easy day today. I'm taking you into the ocean like 1 foot at a time. So right now the waves are only like at your shins. Are you going to drown? You won't slip. Just hang on to me. I'll save you. No, but I'll trip. All right. So last problem. It looks like it's a little bit reversed. This reaction has a K of 1.3 times 10 to the 4th. And the question says, well, what's the K for this guy? And again, we're assuming at the same temperature. Well, we need to figure out what did we mathematically do from here to there? Multiplied by 2. When we multiply by 2, we're multiplying all the exponents by 2. So what do? Raise the K to that same multiple. So today is 2 sig fig day. What is it? I really need to count it correctly. And after counting our fingers on the screen, 1.7 times 10 to the 8th is the answer. So that's everything you need to know about just K and KP, okay? Yay. She's just stretching. I thought she was like waving her hands. And so starting tomorrow, we're going to revisit the rice table from pre-AP. Remember the rice table? No, they're good. These problems would be nightmarish without rice tables. So we'll talk about that tomorrow. So please do your homework tonight and make sure you get K practice. Okay?